let's get started. So so this is the arc we have been on for a while. We started with the Langevin, we did the Poincaré, then we did the Bakri-Emery. Now I want to end this with the log-Sobolev inequality. Okay. So some logistics before I sort of start this. This Thursday, I'm going to be traveling, so there is no class on Thursday. We'll make up some time later on this semester. I'll give more details later. So we saw that the Bakri-Emery criterion implied the Poincaré inequality holds, and because of that, you get exponential decay in the variance. We want to show something similar for the KL divergence. It's a stronger result. So that's basically where we'll finish this up. For this one, I'm not going to give detailed proof. For some proofs, we'll do it, but the rest we'll not do the proofs. Maybe actually I can just put that as a homework. I realize I haven't given you a homework. Maybe your homework is to actually do this thing by yourself. This particular note set, finish it up. I think that's a good homework set. Yeah.
You said this result is stronger than 0.30.
I'm going to talk about it. Today, that's today's class. What I mean by it's strong, we'll show that this implies Poincaré in particular. Okay. Since I'm not going to do the proofs in detail, I think this will be done quickly. I don't know how quickly. So I also have a few odds and ends I want to catch up on. So I'm going to do that. So today's class is sort of wrapping up various theory pieces I will need. And then next Tuesday, we're going to switch. We're going to start talking about various autoencoders and GANs, and then diffusion models, and then the elbow and things like that. So it's going to sort of switch to a different mode where it'll be more algorithmic and architectures. And then we'll switch back to theory after like some few lectures of that. So so this will sort of end this. Today's lecture will end this whole arc for now. As before, I'm still on Ramon van Hendel's book, Probability in High Dimensions. I'm just following chapters 2 and 3 essentially. Same setting as before. PT is a Markov semigroup. Okay. L is a semigroup generator. Mu is a stationary measure. Okay. So let's define the entropy of a function. The entropy of a function is the expected value with respect to mu of f log f minus mu of f log of mu of f. Okay? That's so why is this what's the connection to sort of what you think of as entropy? We'll do this in a second, but first let's just expand this. This means that let z be a random variable with distribution mu. Then it's f of z log f of z, that's the expected value, minus e of z log expected f of z. For those who have done log Sobolev last year with me in advanced probability, this thing should be very familiar object, and we'll see the connections in some time. So in particular, let nu and mu be some two distributions, and such that they're absolutely continuous. So the densities exist essentially, and you can look at ratios without things becoming bad. That's essentially that. So let's f of x be the Radon-Nikodym derivative of the densities exist. It's just the ratio of the two density functions. That's all f of x is. Okay. Then the claim is this: if f is just the ratio of densities, then the entropy, this function entropy, is the same as the KL divergence between these two distributions. Okay. That's the first thing. Okay. So essentially, the guarantees when we give in entropy essentially is a KL divergence type of guarantee. Okay, so what is the KL divergence between two distributions nu and mu? It is log of density of this divided by density of this when densities exist, average with respect to the first one. Yeah, times nu of x dx. So this is just f of x. We'll just write this. We can write this as this divided by mu times mu. So this is just f. So you can pull out the f times mu. So which is nothing but if z, this is nothing but if this is a function, this is nothing but ln f of x times f of x. That's what this is, just that part. It's average with respect to mu. So that means this integral has to be the expected value with respect to mu, which means that this is just this, the expected value of f log f. Okay. So that's what the KL divergence is. It's just this. Now, if you look at this, there are all these other terms. We'll argue that the rest is 0. Okay. Now, in this case, for this particular f, where f is the ratio of two densities, okay, what is the expected value of f? It is nothing but nu by mu with respect to this expectation with respect to mu du x. This mu cancels. The integral of nu it's just a density, so the integral is just 1. And so when I take the log, it's 0. Okay. So that's why therefore, the entropy is nothing but the KL divergence minus 0. So that's okay. So far, so good. That this is all when we say F entropy, with appropriate choice of F, you're going to get divergence results. Okay. So the first theorem here is so-called the modified log Sobolev inequality. I'm going to skip this word modified. We'll see what the exact log Sobolev inequality is, but this is all the modified log Sobolev inequality, but it's a mouthful, so I'll just say LSI. Really, it is the modified LSI. Okay. And the result is the following. So exactly the same setting as before. Then the following statements are equivalent. So instead of the Poincare inequality, if you remember, had connected the variance with the Dirichlet form. Okay. This is connecting the F entropy with not the Dirichlet form, not the F, it's a Dirichlet form of two other functions. The Dirichlet form we looked at previously was of this type. This is log of F. Okay. This is what this is saying. So this is a LSI inequality. It's a log Sobolev inequality. Okay. It's a modified log Sobolev inequality, but yeah, this entropy is less than or equal to C times the Dirichlet form, if and only if the push forward of the function, the entropy of the push forward, decays exponentially. Okay. Very, very analogous type results. Instead of variance, we are just talking about the entropy, F entropy, entropy of the function. So this is also said that it's all the word used for this is entropic exponential ergodicity. Further, let's say that the push forward entropy also goes to 0. It's okay. If this is entropic ergodicity, if this also holds, then we have the following statement. Suppose that you show that the Dirichlet form, so the push forward of the Dirichlet form, which is log Pt of f and Pt of f, then it decays exponentially with and the initial conditions and non-push forward Dirichlet form. Okay, suppose this holds, then this implies these two holds. I mean, if it's one and these are if and only if, so these two hold simultaneously. Okay, so this is what we are going to prove first. So this is the proof I'm going to show. The proof I'm not going to do is the Bakri-Emery analog of this. Okay, we'll come to that in a second. So is the statement clear? This is basically saying if LSI kind of condition holds, then you get entropic exponential ergodicity if and only if. Okay. So first, we recall mu of L of any function g is 0, right? This is what we have seen multiple times. In particular, Pt of f is some g, so mu of L of g is 0. So let's start from there. Okay. So now what's entropy of this function f? It is nothing but expected value of f log f minus expected value of f log expected value of f. That's the definition of the entropy, this function. So let's take the derivative of this, or when instead of f, we'll replace this by Pt of f. So if I take instead of f, I put in Pt of f, I take the derivative, well, we'll do the chain rule. Derivative of, so that means here, instead of f, I have Pt of f, I have Pt of f, Pt of f, and Pt of f in these 4 places. Okay, so d by dt of this, but here's the Pt of f. So derivative of Pt of f equals Lpt of f, forward equation. So we're doing chain rule. It's Lpt of f times log Pt of f plus expectation is linear plus Pt of f times the derivative of this. Okay, let's see what the derivative of log PT of f is. So when I do derivative of PT of f log PT of f, the first term is log PT of f times LPT of f times log PT of f. Second term, when I take the derivative of log of this, it is, so that this one PT of f still floating around. Derivative of this is 1 by PT of f times derivative of this LPT of f. This cancels, giving you just LPT of f. So when I do mu of this, I'll do mu of this and mu of this. Mu of this is nothing but mu of L of some g. So this part is 0. Okay, so that's why you don't need to worry about that term. Are you good so far? So so when we do this part, the second term goes away, which will just give you LPT of f times log PT of f. Similarly, exactly the same arguments, you can show all this is all this part also is 0. So you just get mu of LPT of f log PT of f. But remember the definition of a Dirichlet form of f and g. It is negative of mu f times FLG. That's the definition of the Dirichlet form. So this is g and this is f, quote unquote. So it's the Dirichlet form of this and that. Okay. So this is your basic relation between the entropy derivative with respect to time, the operator is being differentiated. So it's a time. And so it is just negative of this Dirichlet form. So what does this imply? From this, sort of everything else follows. If I look at the entropy of this function f, from fundamental theorem of calculus, it's nothing but the integral 0 to infinity of the derivative of this dt. This is just fundamental theorem of calculus, meaning g equal to integral g prime, okay, over the appropriate limits. Now, derivative of the entropy, we have this expression, stick this in. So we get negative of the Dirichlet form, log PT of f dt. We are assuming 3 holds. What is 3? 3 statement says the push forward Dirichlet form. Let's go back and see the definition of 3. The push forward Dirichlet form, exponential decays. That's the statement of 3. So push forward Dirichlet form, the exponential decay times the initial condition. This has no t in it, this block. So it's just the integral of this exponential, which is just a constant c. Okay. So entropy 3 implies 1 says the LSI is true, meaning this is less than or equal to this.
Leave the fact that entropy of PT of f is going to 0.
For 3 implies 1, because of this. Because of, otherwise f prime of 0 is 0. The end conditions. To use that end is 0. I'm using fundamental theorem of calculus. I need to get the other side to be 0. So really, it should be this minus the other one. That is 0, and that's why it's written this way. Okay. Now 1 implies 2. So 1 was saying, let's go back to 1. That the LSI is true. The entropy of the function is less than or equal to c times this Dirichlet form, log ff. Okay. So we want to show this implies decay. So derivative of the push forward, entropy of the push forward function from our, we had this basic relation we just derived. It's nothing but the negative of the Dirichlet form of log PT of f, PT of f. And by assumption, well, this is essentially, this is just restating the LSI statement. The LSI states that this is less than or equal to c times this. So when you put the negative sign and rescale, you get this. Okay. So 1 implies 2. 2 implies 1 is similarly pretty straightforward. So start from the Dirichlet form, write it as a limit from star. Remember this equation star says this equals negative of that. So this derivative of time, we'll write it as a limit. Time tends to 0, entropy of F minus entropy push forward of F by T. But now we know that this thing decays exponentially in time. So this is equal to e to the minus t times this. So this is 1 minus e to the minus t over c by t. You take the limit, you get c. So this proof is just, once you saw that relation between sort of, the key was the first step. Okay. After that, everything else is sort of just pushing things. Okay. Let's do, so this is the basic LSI equivalence that if a modified LSI, yes.
In the very first,
Mm-hmm.
you're using fundamental theorem.
Yes.
But shouldn't it be d by dt of entropy of PT of
Why? What, this is just F. Where is PT?
no, in the integral?
Oh, wait. Yes, I've written it wrong. It should be PT of F. That's why P infinity of F is the entropy. That's, you are right. There's a typo there. That is the fundamental theorem of calculus. There is no minus sign. There is a minus sign. There is a minus sign. Well, does it mess up anything else?
Then the next thing becomes a plus sign.
Then everything breaks? No, because e to the minus c. I see. This is still correct. Okay, fine. Thank you. Okay, I'll upload this after I'm done. Okay. So let's do this calculation for the Gaussian to see exactly explicitly what's going on. Also, we will see where Gaussianity is used. Again, let me finish this and then we'll get to this. So let's do the scalar case for simplicity. So mu is just a Gaussian, one dimension d equal to 1. So it's a Gaussian with 0 mean unit variance. And the associated OU process is dxt is minus xt dt plus root 2 bt. In this case, we remember that the Dirichlet form is just the mu of f prime g prime, which is nothing but or you can write it the inner product of f prime d prime, where these primes, whenever I write prime, is d by dx, not d by dt. Okay. And most importantly, for this, the push forward of f prime is e to the minus t times the push forward of f prime. This we derived where we use explicitly the Gaussianity, we use the structure of L to get this one. Okay, so this is true more broadly than just Gaussian. In fact, for any Langevin dynamics, you know that the Dirichlet form is of the form grad f inner product of grad f grad g with mu. But the second statement is very Gaussian specific. Okay. So in this case, we'll explicitly show that you get the LSI with you get the LSI inequality with parameter half. Okay. So first, when I need to compute this, there's an L. So I need the. Okay, let's just do a side calculation first. So first, observe the following. If I have these derivatives all with respect to x, it's a scalar system. So log g derivative times g derivative. So this one's derivative is 1 by g times g prime. This g prime. So it's g prime square by g. Therefore, if I do a push forward, instead of g, I do a push forward of f, then I will get instead of g, pt of f prime, pt of f, I get the e to the minus t because of this. The derivative of pt of f prime is e to the minus t times pt of f prime. So, all right. So I'm just using this along with the Gaussian property here to get this. Okay. So therefore, next, pt of f, this one. I need to look at this. So we can write f prime as f prime divided by root f times root f, and then Cauchy-Schwarz it to get pt of this times pt of this square times pt of this square. Okay, that's next step. Now this we have seen is equal to this, so we substitute back log f prime times f prime pt of f. Okay, so this is finally what we have. So if you put these two together, let's shrink it a little bit. Then what we have is log of pt of f prime times pt of f prime is e to the minus t. Then for this, you substitute this in, this pt of f and this pt of f cancels, just giving me this. Okay. So that's where we are at. The reason we have this, we are interested in this, is because for the Dirichlet form calculation, you know, there's a log pt of f and a pt of f. So that's what, yes. Is that a mistake? PT on this and PT on that. So I'll do the Cauchy. No? It's all time derivative.
Yes, but here, like, you can't, so you're doing Cauchy-Schwarz on the inside, but how are you splitting the PTs after that? Because PT is acting as an operator on F, but that doesn't mean you can split it.
It's like a conditional expectation.
It's just a PT is just a conditional expectations. I will do the Cauchy-Schwarz with the, I do the conditional it's a conditional expectation, PT of x for each. That's it. So I'm doing the expectation version of the Cauchy-Schwarz. E of xy less than or equal to expected value of x square. E of x, expected value of x square times the expected value of y square. That's the version I'm using. Square root of that. Okay, where was I? Here. Yeah. So therefore, the Dirichlet form of log pt of f and pt of f is nothing but the expected value of gradient of this times the gradient of that, times, there's a push forward. Wait, did I miss a push forward somewhere? Let's make sure I didn't mess up something. Just give me a second. Is this wrong? LPT of f. Give me a second. I want to make sure I didn't mess something up. No, this is correct. This is correct. Okay, it's just the derivative of each one times. The L is already taken into account in this business. Okay, fine. So it's, the Dirichlet form here is this one's derivative times this one's derivative, average with respect to mu. Okay. And now I just stick this in for this. So we'll get e to the minus 2t pt of this. Pull this, this is an averaging with respect to the x variable, so I can pull the e to the minus 2t out. I'm starting from the stationary distribution, so mu of pt equal to mu. So it's mu of L of f log of f prime times f prime. So that's where we're at. And this is nothing but the initial Dirichlet form. So we have actually shown that the step 3, essentially, if you remember, which is log pt of f is less than or equal to e to the minus t, the initial Dirichlet form. And now from this theorem, we get the LSI. So in this case, we can explicitly show the LSI for the Gaussian case. Of course, critically, all this was doable because of this step. Okay, that for the Gaussian OU process, we explicitly computed what happens to PT of f prime. This used the structure of L. We cranked through this in a previous lecture and got this. Okay, if you have a generic Langevin dynamic, then you don't have this. And so the same kind of story holds as before, that it's not easy to see that we can explicitly show what the LSI equality is, which is why the Bakri-Emery criterion comes in, and we can do exactly the same kind of thing. But before I do that, let's do a couple of other statements. So we have shown this for a scalar case. You can imagine proving exactly the same kind of thing using vector calculus. Instead of derivatives, look at gradients, do exactly the same thing will hold. The other way to do this is use tensorization. Okay. If you want to see, in this class, I'm not going to go down the tensorization route, but it's in the other class I taught in advanced probability, we did essentially by tensorizing. We sort of look at tensor products and lifted over dimensions to get these things. You can do a similar type of proof, you'll get it. In fact, that's how we prove the LSI there, using a tensorization argument. Okay. In fact, the theorem statement is the following in general, that the vector version of it is the entropy of the Gaussian, for Gaussian, the modified log Sobolev inequality is entropy of f of x, where x is a d-dimensional vector. The parenthesis missing is gradient of f. Yeah, it's just half expected value of gradient of f norm square. There's also, again, I'm not going to prove this. We have this machinery also implies concentrations for Gaussians. Okay. If you're interested in the proof, you should look at chapter 3 in Ramon van Handel's book. That if you have x1 through xdb, some IID Gaussian random variables, and fb any f be a function such that sigma square is the L infinity norm of gradient of f square. Okay. Then f minus e of f greater than or equal to t decays as e to the minus t square. Okay. So we have done these kinds of things in the other class. If you're interested in going back and looking at the notes, it's on my webpage. You just click on advanced probability and you'll see the notes for these kinds of things. And so I want to sort of just step back and look at these things qualitatively a little bit. What we have is entropy of f, which is defined as mu of f log f minus mu of f mu of log f, is less than or equal to half of the Dirichlet form. That's basically what the modified log Sobolev inequality is. If instead of f, we look at the function f square, okay, you can always use the function. You can write g equal to f square and use the same function. Then you can rewrite this as the following: half entropy of f square equal to mu of f square log f, the minus mu of f square mu of log f, okay, less than or equal to EFF. In the Gaussian case, you can rewrite this. And so the Poincare inequality, so said the following. So in this Gaussian case, the Poincare inequality said that the variance, which is E of f square minus E of the whole square, less than or equal to C grad f whole square. The LSI, now you can see once you sort of rewrite it this way, is slightly stronger. It says E of f square log f minus E of f square E of log f is less than or equal to C times grad f square. So now you can look at the Poincare with the LSI in a very similar setting. And you can see that there's an extra log f. And this extra log f gives you stronger concentrations in the concentration setting. So if you just had a Poincare, you would have got at sub-exponential concentrations. That is, the decay would be e to the minus t. Whereas the LSI will give you sub-Gaussian, meaning it's e to the minus t square, the exponent. Okay, yeah. It is just grad f because the Dirichlet form, there should be an expectation. There should be an expectation, right? Yeah, there is some integral missing there. Okay. Correct. So this extra log f gives you faster concentrations in the when you look at just concentrations, and when we look at sort of mixing, we get from variance to entropic. So so now you can see the connection between the Poincare and LSI, and you can see sort of qualitatively is that if you have this, then it should quote unquote imply this. And indeed, suppose that the entropic inequality LSI holds, then we have the Poincare inequality is true. Okay. Once you put it that way, you can see that. Okay. This statement, by the way, is not Gaussian. All that was intuition with Gaussian. This is now we have just stepped back more broadly. Again, I'm not proving all the details here. We are just sort of going through these pieces today. Okay. Finally, analogous to the Poincare inequality story, we have a Bakri-Emery story here again. Okay, meaning let PT be a reversible and ergodic Markov process with station pressure mu and semigroup generator L. Okay, this is your homework problem. You're going to prove this theorem. Okay. Then remember the Carré-Duchamp, the gamma function fg f comma g in the cases we cared about was equal to grad f dot grad g. The Carré-Duchamp was that. Okay, that's what we had for in the special case where it's a Langevin dynamic. That's what we showed last time. We actually explicitly showed that. But suppose that this following property holds. When you, for any function phi, look at the composition of phi and g. Suppose that the Carré-Duchamp has this property. Okay, this looks really opaque. So let's see what this actually means. Okay, let this be grad f dot grad g. Then let's look at what is gradient of this mean. So grad of phi g, phi composed with g, means the gradient with respect to x of phi of g of x, which is nothing but phi prime of g of x times, so x is an RD, times gradient of g of x. So now this is nothing but, in the same notation we're using, this phi prime composed with g, but this is just a scalar, okay, times grad g. Okay. So gamma of f phi composed with g is grad f times grad of phi composed with g. That gives me, as from this side calculation, this scalar times grad g. This is a scalar, so I can pop it all the way out, which is just phi prime g grad f dot grad g, which is just this. Okay, so that's what this condition, we are assuming this condition holds. You can see that what this condition means, that you can do this kind of a thing. Okay, so what you're going to actually prove is 3 steps. You're going to prove these 3 steps. I'm just going to show you those 3 steps. The first step, so we are interested in looking at this. What we want to show is the following, that suppose the same Bakri-Emery criterion holds, which is C times lambda to the iterated gamma function is greater than or equal to the gamma. That implies the modified log Sobolev inequality. This is what you're going to prove. To do this, you're going to go through 3 steps. Yep. The first step is start from the Dirichlet form of the log of PT of f and PT of f. Show that it can be written in the following form. Importantly, this is the term I wanted to focus on. It is the gamma function of the push forward of the log of the push forward. Okay, push forward log of the push forward. So this is the first thing you're going to show. Once you show this, you're going to use the Bakri-Emery criterion to simplify this. And the way you're going to simplify this is just like what we did in the Poincare calculation for the Bakri-Emery. You're going to take this and show that this PT can pop out. If you remember, that was one of the key steps when we were doing in the last lecture. So effectively, that pops out, which will give me that the push forward of the gamma function of log PT of f log PT of f. So this PT somehow pops out, okay? And you're going to use this to do that. Once you have done that, then you're going to further simplify this and show that this thing further simplifies as basically just the Dirichlet form of log PT of f, PT of f. So you're going to essentially show these 3 steps. And this, look at this. This is the same on both sides. So this basically goes away and becomes a half. So I can square everything, which basically gives me this. Okay. So essentially, the Bakri-Emery criterion here implies this. Okay. This is going to be your first homework problem set. You'll just work through these steps. The machinery is essentially the same thing you did previously, but you just need to do, yeah. You need to be very careful. And finally, now that you have this, you can see that again, if it's rho strongly log concave, then exactly like before, what you're going to show is, we have already shown this actually. If it's rho strongly log concave, you've shown that this holds. In fact, we proved that. This has nothing to do with whether it's a Poincare or whatever. We showed the Bakri-Emery holds last time. And therefore, using this machinery, you've got that you can get KL independent of dimension for measures which are rho strongly log concave. You get essentially exponential ergodicity in KL. Okay. So this is the whole arc of for such distributions, at least with standard Langevin sampling, we have shown exponential convergence. Okay. So this ends this whole storyline for now. We'll come and revisit it like in a few weeks maybe, but for now we will stop. Yes. Yeah, all that kind of. I just haven't gone down all that. There's some way. Yeah, there's. Okay. I put that story up in that place, but there's all these conjectures around. Okay, so what I want to do I have about half an hour to 40 minutes, to about half. I only went through half. That's what I figured. They just because I didn't do proofs, this would be only half the class. I want to tie up some odds and ends which are needed later. So that's what I thought I'll do today, instead of starting the next piece, which is very because that requires a completely different mindset. It's not a. It's much more architecture and how design choices. So I don't want to start that today. So I'll just wrap up a few other things which needs to be done, which will be useful again in terms of proofs. Okay. So we have seen this. Yes.
We've gone over relates to the like modern derivative stuff like PDPM and all that.
Good. Right now, it just looks vaguely connected, and we need to make these connections more concrete. I'll tell you what I mean by vaguely connected. What we'd like to do is you would like to sample from some high-dimensional distribution. Generative models are using some sort of annealed Langevin dynamic to actually do the generation. It's much more nuanced than that because it's actually doing it in the latent space of AVE, so we need to get to all that next. But ignoring those issues, is what a generative model, a diffusion generative model does at a high level is start from pure noise and run some annealed version of a Langevin. This what we have analyzed is an unannealed version, but it'll run an annealed version of a Langevin. And at the terminal, we are essentially sampling from the image distribution. Whenever you start thinking of sampling, the key questions are, what is the stationary distribution and how far does it mix? So before we get to annealed problems, let us look at the state of the art of how this. I use this arc to sort of develop the machinery to start thinking about these type of problems for the simplest version of it, which is the unannealed version. Okay, and that's basically what this theory is. So we now know the machinery needed to start looking at analysis of sort of some annealed types of processes, which we'll come back and revisit. So there are a couple of things we need to do. One is we are actually working with annealed processes. Second, we are not working in continuous time, we're working in discrete time. Both of those are non-trivial to deal with mathematically. And we will deal with both in the next. After I finish sort of setting up the problem of where the autoencoders play in, why are we even using this kind of an architecture, VAs versus GANs versus diffusions, how is training of these models done, and then we'll come back and address these issues. Does this help? So think of this as a sort of the simplest type of setting you could think of to see what kind of machinery we needed to develop to understand, and so that we can start doing this for other types of problems. Good. the next thing I want to talk about, in the Markov process class, towards the end, I talked about sort of different metrics, okay, which I don't think I sort of rushed through it. It wasn't, I just defined a few things like Fisher information and so on. Today, we again define the KL properly, so we are good there. I want to revisit the connection between these objects we are going to play with and see how these things are related. Essentially, we are going to play with the score a lot. You've already seen that the score is very important in any of these Langevin things, because that's what your drift field is. It's an unannealed score. It's just the standard score function, which is grad log pi star of x. In reality, also looking forward to your question, that's not the score function we are going to use. We are going to use a Gaussian annealed score, meaning we are going to look at this particular object a lot. Okay, so suppose that I want to sample from the distribution P0. So that's x0 is the random variable associated with this. It's a d-dimensional random variable. Think of x0 as a typical image if you want to look at an image example. Okay, so in which case d is, if you're looking at no autoencoders, no latent space, nothing, then d is order of 3 million dimensions. So that's the size we are thinking about. Okay, the way it's a 3 million dimensional vector is it's a 1024 by 1024 image. It's in 3 colors. And so when you just stack it all up, it's a 3 million dimensional vector. Okay, this is what we want to sample from. But this is not the score we are going to deal with. We are going to actually use a Langevin-like thing, which will use the score of a smooth version of this. And what I mean by the smooth version of it is add a Gaussian to it with some controlled variance. Okay, so Z is always identity covariance. So we can always, so sigma will tell me the amount of noise variance you're adding. Okay, so you convolve this with this, and x sigma is the smooth version of x0. Okay, and for any particular sigma, I'm not now defining dynamics. I'm just looking at a static problem. Fix a sigma and look at the score associated with it, which means it's grad log the density of this one. Okay. So this is an object we are going to use a lot. Okay, in any of the algorithms, we are going to play with this. So it's worthwhile to understand how this is connected to various things we are maybe comfortable with. Okay, and in this process, I will also show some basic relations between score and some other objects, which are going to be useful as sort of in proofs later, that the score is equal to this and so on. So there are 3 relations which are interesting. Today, I'm going to just prove one of those 3, but I'll show you all 3 of them. Okay, so the objects we care about are the score. But before I get to that, sorry, I jumped ahead. So let me tell you where all this is from. So first is the proof I'm going to show today is sort of Professor Krishna. It's not this particular proof actually was just when I was visiting College Station last month with Krishna. He basically, between him and me, we sort of derived this thing out. It's not a new result or anything, and Krishna did most of the work, to be honest. So this is Krishna's proof. But this is actually a very old result, it turns out, by Brown, Annals of Mathematics, MathStat in 1971. And some of the other papers which are interesting is also by Dongning and co-authors on something called the MMSE paper, which is very well known in information theory. Okay, so these are the references. So we are looking at the following objects we are going to try to talk about today. The first object is the score. Okay, as I said, what is the score? It is the score of the Gaussian smooth version of this density function. Meaning, take x0 from whatever the base density function. This is the equal. So p0 corresponds to pi star we have been dealing with all along so far in this class. Okay. So take p0, noise it a little bit, meaning add a Gaussian with some standard deviation sigma or variance sigma square, and the resulting density is nothing but the convolution of this with that of a Gaussian with variance sigma square. That's all P sigma. So P sigma equal to P0 convolved with N0 sigma square I. Okay, that's what it is mathematically. This is an independent Gaussian. The score is grad log of that density function. Object number 2 is the minimum mean square estimate. Suppose I was asking you the following problem. I give you this, I tell you that I take random samples x0 and noise it and show you x sigma and ask you to estimate x0 to minimize mean square loss, okay, the square loss matrix. Then we know that the conditional expectation is the optimal mean square estimator. Okay, this is what you've seen in your probability class. So the second object we are going to talk about is the following. Look at the conditional expectation of x0 given that you can observe the noisy version. So this is a denoiser. I've given you a noisy image and ask you to estimate the clean image, okay, in the squared loss sense. So that's what this is. And it's parameterized by your observation x sigma and the noise level that was used in this. So these are the two parameters for this. So this is what we'll call MMSE of x sigma comma sigma. Good so far? The third object we care about is the Fisher information. The Fisher information is it's nothing but the expected value. So this is what I defined some time back in that last bit of the Markov process when we defined. So given a distribution P sigma, the Fisher is nothing but the expected value of the score average over the distribution, score square. Okay? These are three objects. And so now the question is, how are these things related? The first relation, today I'm not going to prove this. When we get to DDPM and we will sort of derive this again. The first relation is between score and the MMSE estimate. Okay, this is a very, very important estimate. This is actually, of these three, the most useful for practice. It tells us that the score is affine in the MMSE estimate. Okay, meaning if this is meaning if you observe x sigma, then x sigma plus sigma square times the score evaluated at this point is the MMSE estimate. This is very, very useful because neural networks are great at solving MMSE problems. Okay, it solves a regression. Essentially, you can think of neural network if I give you a training set of image comma noisy image pairs, then I can use that to solve the regression problem, the conditional expectation, and the neural network approximates the conditional expectation. So this is something that can be used. This can be using sort of standard training. You can presumably approximate this function very well with lots of data. We'll get more technical with this, but roughly, this is something which is potentially doable. This is what I need for various reasons. Most importantly, because this is when you're doing diffusions, I need to know the score. So this gives this relation gives me a way of estimating the score. Okay, so essentially a denoising network in a diffusion is this. It is if it wants to find this, it is some function of MMSE subtracted with x sigma scaled and so on. Okay, so when you're doing denoising, you're essentially using this critically, this expression. We'll come back to this and look at it more carefully in some time. So this is one expression. These other expressions are useful for proofs. Okay, so which is what I want. So this, I want to push this to a later class when we're actually starting to talk about how these algorithms work. So we'll prove it at that point. Okay. The other expressions are the following. So we have the MMSE estimate, and associated with the MMSE estimate is the MMSE error. Let's call it script E of P sigma sigma, which is nothing but given x. So what's the MMSE problem? Given x sigma, I want to estimate x naught. Okay, so 0 basically means unnoise, sigma means noise level sigma, which is nothing but the conditional expectation of x0 minus x0 given x sigma. This is my estimator. And this, so x0 minus this is nothing but x0 hat. So this is my estimation error, squared loss. So this is nothing but the MMSE error itself. Okay. And this is the relation we are going to prove today, that the MMSE error and the Fisher are affinely related. Okay. So meaning, well, I don't know whether this is the relation. It's I don't know whether I call it affine or linear. I'm not sure what to call it, but whatever. It's sigma square times dimension minus sigma to the 4 Fisher is equal to the MMSE error. We will prove this today. This is this is from the paper in Brown's identity. The third relation, which is really interesting and we'll use it for proofs, is the IMMSE relation. So what we did here is to look at a signal and control the level of noise we're adding. Equivalently, we can keep the noise level fixed and change the signal strength. Okay, it's some rescaling of a different type. Is it clear what I mean by that? So previously I was looking at x sigma is x0 plus sigma z. I can instead I can keep the noise always fixed and just scale down the signal strength with a rho. Okay, so I can write y rho is rho x plus z. Okay, and then what the IMMSE relation relates the mutual information with the MMSE error. Okay, it basically says that d by d rho, if I look at how the mutual information between x and y sigma. And what's the mutual information? It's nothing but the KL divergence between the joint distribution and the product of the two marginals. So essentially it tells you how much predictable, yeah, right? How much if the KL divergence is 0, that means y has no predictive ability on x. Okay. So look at the derivative of the mutual information with respect to this, with respect to rho. Okay, how does this change as the signal strength changes, essentially? Okay, that is equal to rho times the MMSE error. Okay, this is called the IMMSE relation, and this follows from De Bruyn's identity. We'll come back to this. Again, we'll look at this. We're going to use this in proofs later. Okay, the way we are going to use this in proofs is the following. We are looking at, so far, everything I've talked about is in continuous time. We need to discretize in time, which means in every discrete time step, there is some accumulation of error that is happening with respect to the continuous time system. You need to bound how much that error is happening. And this is going to tell how much stuff is decaying over that period of time when you're being denoised, essentially. And we will actually use this particular relation to start developing bounds. Okay. So these are the three very interesting identities. Today, I'm just going to prove one of them. Okay. The other two we will deal with at different times in this class. So we are going to prove that the MMSE error and the Fisher information are related in this following way. So let's do the proof. So the MMSE error, so first the MMSE estimate is, we'll start by assuming the Tweedy's identity. I know I have not proved this, but we will sort of prove it at a later class. Let's take this, that this is true on faith for now. Okay, that this relation we're going to assume holds. Okay. So this is the MMSE estimate. It's equal to x sigma plus sigma square times the score. The Fisher is nothing but the average of this norm of score square. Okay, so if I substitute this minus x0 divided by sigma square, that's what equal to the score. Substitute that here, we'll get this thing minus this thing square, 1 by sigma to the 4 because it's a square in there. So E of x0 given x sigma is just, we'll call it G function. G is my guess. It is my MMSE estimate. Okay, this is nothing but my estimate of x0 given x sigma. We can change variables. This is over this is the expected value over x sigma, the noisy distribution. But this is the same thing as I can look at it over x sigma equal to x0 plus sigma z. This is an independent Gaussian. This is from P0. So I can equivalently look at the joint of, I can go back to the original space of x0 and z and write this expectation as the expectation over two variables. That's the guess function, which is a function of x sigma, but x sigma is equal to x0 plus sigma z. So we have written that x sigma equal to x0 plus sigma z. That's all that happened here, nothing else. Okay. We'll take this x0 of this part, put it here, leave the rest alone. This then is guess minus x0, which is nothing but the sample estimate error. It's a function of x0 and z, okay, minus sigma z. We are not doing any expectation change. We're just doing random variable by random variable. We're just looking at this. Let's expand this norm. This is nothing but the first one square plus second one square plus the inner product of this and this. Minus, sorry, because of the negative sign. This square plus this square minus 2 sigma times the inner product of this error and z. Okay. So let's look at this particular expected value of this inner product. So the inner product of the error of x0 and z with respect to z. So again, what is the error? This is x0 hat is guess, which depends on x0 plus sigma z. That is the same as guess of x sigma. We can write it in all these ways. So it's this inner product of x0 and z. We'll change the variables from x0 and z to x0 and x sigma. Okay. So the error is a function of x0 and z. It was defined as x0 plus sigma z minus x0. I don't want to deal with z. I want to deal with x0 and x sigma. So we can write this as a new function g at e hat, which is guess of x sigma minus x0. Okay. Basically, there are three variables. Given any two, the third is deterministically known. So we need to do the right integration of the right two variables. Some are easier than others, and we'll be switching between these, some two of these three all the time. So z then, the noise is x sigma minus x0 divided by sigma when you do this change of variables. Therefore, when you do this change of variables, expected value with respect to x, where the x0 and z, instead I can write it as expected value with the variables x0 and x sigma. So the joint distribution, whenever we are doing this, the joint distribution is changing. Okay, so we need to change all the functions correctly. So this function becomes this function, this becomes this. And now it's over this joint distribution. Okay, so we have this x0 minus x sigma minus x0. We can write it as, we can add and subtract g of x sigma. So where are we going with all this? I'll show you in the next step. We have just added and subtracted g of x sigma in this expression. Good so far in terms of just algebra? Okay. So this, let's look at this for a second. What is this? This is nothing but x0 hat minus x0. This is the optimal estimator in the mean square sense. So what does principle of orthogonality tell you from your random process class? It says that the error vector is orthogonal to any other estimator. Okay. So if I give you some information and I use the MMSE estimate, that is the conditional expectation of x0 given x sigma, given x, then I can try to estimate x0 using some other function h of x sigma. Principle of orthogonality says x0 minus x hat is orthogonal to h of x sigma for any h. You can't improve the estimate anymore, essentially, once you have done the conditional expectation, right? That's the ortho. So let's do that now. So you can think of this as some estimate. It's some function of x sigma, and you could just sort of think of this as some way you're trying to estimate x0 from x sigma. Okay? It's some function. So therefore, you know, the inner product of this and this is 0. Okay. So that's the principle of orthogonality. So this, the inner product of this and this is 0. And so let's go back here. We had this. This equality then becomes just inner product of this and that. This part goes away. This is what we have written here. So that expectation can be written as inner product of the error and g of x sigma minus x0 by sigma. But look at this. This is the same thing on both sides. So it's just a squared error. This is a scalar thing. 1 by sigma pops out. It is just the squared error of g of sigma minus x0, the whole square, over x0 and x sigma. We popped this whole thing out. Where did we get it from? From here, where it was in the space of x0 and z, everything else in the x0 and c. So we just looked at this particular term. We went to a different space of x0, x sigma, analyzed it, and simplified it. So we need to now bring back the resulting back to x0, z space. Okay, so we had an x0 sigma space. Let's bring it back to x0 z space. In that space, then, using our previous notation, this is nothing but the error with respect to x0 and z. So what does this lead us? This whole chain has given us the following, that the Fisher information, remember that was the expected value of this score square. This score, we used Tweedy's formula to write it as the condition expectation minus x0 square divided by sigma to the 4. We went through all this, we expanded the square, looked at this third term, we did all this stuff, used principal orthogonality, and brought it back here. Okay. The third term now is just it's essentially of the same form as this first term, meaning this one and this one cancels, this just gives a negative sign. It gives 2 times that. That's basically what we have shown through all this. Okay. So therefore, the Fisher information is equal to 1 by sigma to the 4, the expected value minus of the error square plus sigma square times the norm of z square. Z is a Gaussian. 0 mean unit vector Gaussian, right? So what is the norm of z square? It's just d. It's just the dimension. Okay. It's a d-dimensional Gaussian identity covariance matrix. So its norm is just d. Expected value of it is just d. So this gives me the proof of Fisher information is equal to Fisher information is related to the MMSE error. And this is called Brown's identity. It goes back to 70s. But so it's cool because there are these 3 objects, and we are going to we see how closely related these objects are, and we'll use this in analysis later. These quantities, and always bringing it to MMSE is something very nice because this is something we understand very well from various other areas. So if you can bring sort of these objects to something related with MMSE, it's much easier to work with. Okay. So that's the thing. The other now, the relation is the IMMSE, which I just said, which is nothing but the derivative of the mutual information with respect to signal strength is also related to the MMSE. We'll actually use this in the integral form. So we'll use fundamental theorem of calculus and write the difference in the how does the mutual information change as the signal varies, strength varies, and write it as the integral of the MMSE error. And we'll use some monotonicity properties of the MMSE error, which is decreasing, to actually get bounds on how mutual information decays. And we'll see that that's really important sort of for showing discretization bounds downstream. But this is all sort of in the next sort of theory block, which I'm going to do. At this point, we have sort of built up enough sort of machinery to see what are the kinds of questions we should be asking about algorithms. That's really what we have done so far. And for next class, I will talk about actually how these algorithms are, meaning we'll start about autoencoders, we'll deal with GANs, we'll do diffusion models, we'll derive 2D's formula, how do you learn this stuff, and then what's the loss function, something called the elbow, and so on. So that's basically starting next Tuesday. So I know that it's sort of 10 minutes early, but I think this is a good place to stop in this arc. So yeah, we'll continue from this next time. Thank you. And Thursday again, I'm not going to be teaching. We'll meet again 1 week from today. Thank you.